Hello and welcome to DataCast Solutions, Statistics and Data Mining 101 using Knime. In this chapter, we're going to revisit the topic of ensembles in slightly more detail. Now we're going to rehash some of this because when we discussed random forest and gradient boosted trees, we did talk a bit about ensemble. So I'm going to walk through in just a little more detail some of the topics behind it. So a reminder, ensembles is the process of combining the outputs from multiple models into a single decision. The model's been created using the same algorithm or with different algorithms. Why do we use ensembles? Well, first and most importantly, accuracy. They're usually better, more accurate at least than individual models, and often different algorithms achieve the same level of accuracy but on different cases, and so identifying different ways to get the same level of accuracy. They are reliable. They generally they don't rely on a single model or a single prediction. Think of it like a committee of experts. And finally, automation. These days with Knime, it's very easy to build an ensemble model. There is definitely wisdom in crowds. You get a diversity of opinion by different algorithms. It's decentralized, so each thing can be independent of one another. And so, in other words, multiple analysis. They're independent. You can use different sampling and different algorithms, and you can do aggregation. So you can do this by voting and have each model vote what they think the answer is, or you can use weighted averages to give certain models more input than others. Some of the taxonomy we're going to be seeing here. So stacking method is a meta models. Bagging is going to deal with low bias and variance reduction. And then boosting methods are going to be for bias reduction. Heterogeneous methods are going to try to take average predictions from multiple models. And stochastic gradient boosting and random forests. And we're going to talk a little bit about all of this. Now a review from what we first covered when we talked about random forests. Bias is the average distance between our estimate and the true mean. And when we have a large bias, the model is too simple and it does not fit the data well. Variance is the squared deviation of the predictor around its mean. A large variance means the model is too complex so that small changes of the data, in other words, a large variance is going to mean that you've overfit. So look at this example of some data for some values over time. And the first chart here on the right, we see a large bias but a small variance. It's a very simple model, basically a straight line, but a large bias because most of our data points are far from the mean. Now, in the bottom left, we see a moderate bias with a moderate variance. The line is a little complex, but we've kept our points closer to the data point. And then finally, a small bias where the numbers are pretty much right on the line, but a very large variance because this model is overly complex. So different ensemble methods tackle those two problems. Variance reduction, we use the techniques of bagging and random forest and heterogeneous ensembles. If we're trying to reduce bias, it's going to be through boosting, arcing, or stochastic gradient boosting. Which models do well in ensembles? Where decision trees, naive Bayes, neural networks, KNN, and SVM all do fairly well with ensemble techniques. The marginal ones, linear and logistic regression, KNN were the high, with a high K number, and LDA are going to be less effective. I love this pictorial because it helps you really visualize this. Ensembles smooth the jagged decision boundaries between two classes by using those weighted averages or voting mechanisms. It smooths those boundaries because every algorithm builds its own decision boundaries. Not all nonlinear classifiers create the same nonlinearities. So take a look at the smoothness of the support vector machine and the quadratic nature of the naive Bayes and the jagged nature of KNN. These are good examples of why blending those three techniques together smooths it out. And yet another visualization of the same data set using different techniques. And when you look at it that way and see them plotted, you can see how each technique produces a different set of boundaries. And this is again where the idea of the ensemble can help smooth that out. So the bagging method, it's an ensemble learning technique that creates multiple weak predictors and then combines them to a single aggregated predictor that may lead to better predictions than each of the individual ones. Each predictor is created by training a model on a different representative part of the data. So even though each of the predictors might make a bad prediction on its own, as a collection, they're often able to do better with the model's underlying concept. So to create a strong predictor, the weak predictions are aggregated using one of many different methods, such as taking the mean of a numeric prediction, or using the class that was predicted by the majority of the predictors if it's a classification problem. So here's an example of bagging. We've got an original data set, and we're going to create many data sets by bootstrapping it. You could also do this with the cross-validation node in Knime. And we're going to create one decision tree for each data set. Then we're going to combine the decision trees by averaging the final answer. So this primarily reduces the model variance rather than the bias. And on average, this is going to produce better results than any individual tree. The ensemble method in Knime is going to involve splitting the data into chunks, collecting the models into a table, and then iterating the table in another loop and applying the model on the input data. Afterwards, the prediction results need to be collected, and a voting loop calculates the final prediction. This is a very simple workflow, but it shows how what we can do to learn and predict using the bagging method, which creates the ensemble. We start at the beginning by shuffling the data, and then we use the chunk loop start where we're going to break this data into chunks. And each model is then, you see there's a decision learner within each chunk. But it ends with a model loop end, which is collecting all of the models together. The model loop end is going to feed a model loop start. And that's where we're going to take our testing data. The training data fed the first loop. Our testing data feeds the second loop to the decision tree predictor, which is going to run through each of the model loops. And it ends with a voting loop. And the voting loop is going to create the aggregation of our predictions. The bottom half, by the way, you see a slightly different permutation of it where we're generating a PMML model so that you can export this prediction into any other tool. Another mechanism we have, of course, available in Knime is the tree ensemble learner. They built this module afterwards, so it's no longer necessary to go through the individual loops. You can work with it together. That's something that we actually covered in a previous chapter on ensemble learning with random forests. As you can see in the output, I've got decision regions for 9 bagged trees. And then the decision region for the bagging ensemble, you can see how it's blended that together to come up with basically a better model. Another ensemble learning strategy that can be used with Knime is boosting. The AutoBoost algorithm. As outlined in the earlier introduction, the AutoBoost algorithm assigns a higher weight to records that were misclassified in previous iterations. and then in subsequent iterations, they're chosen based on that weight. Therefore, records with a higher weight are more likely to be chosen the second time through. So consequently, the next base of the learner focuses on patterns that were incorrectly identified the first time. So boosting is going to create different trees using the same training data set over and over again. It's going to score each data point, and it's going to indicate which decisions were made in error. And then it's going to retrain those rows with incorrect decisions based on that weight and keep repeating. So the final prediction is a weighted average of all the models. This is best to create weak models, simple models, like in a decision tree, just a few layers deep. And it's often used primarily in decision trees and naive Bayes. But it's usually a much better result than individual trees or bagging. For boosting, Knime offers pre-configured metanodes, which in turn set up a boosting workflow into a fairly straightforward process. The two special metanodes are the boosting learner and the boosting predictor, and they'll support this workflow. So the content of a boosting learner for like whether you're doing a multi-layer perceptron neural network is shown on the next slide. Take a look and we see the input of the boosting learner loop start is a data table that contains the trained data. And then in the loop, we're doing the RPROP MLP. This is our neural network learner, and it trains the model and it does the prediction, and then the boosting learner loop end. So it's going to go through this process of going through it over and over again, each time doing the boost. And then finally at the bottom, the associated model, once it comes out of it, is going to feed the boosting loop, the boosting predictor loop start, which will generate the actual prediction, and then I can feed directly out into the score. Now, of course, I did that example using a neural network. I can use naive Bayes. I can use any model that supports decision trees, etc., and they'll all work with the boosting technique. And finally, a reminder, we went through an entire chapter on the random forest and explained how to do it in detail, but it's the exact same methodology as bagging, but with a twist. At each split, rather than using the entire set of candidate inputs, use a random subset of candidate inputs. So it generates diversity among the samples. And on average, this gives a better result than individual tree bagging or even boosting. So it tends to be one of the first things I turn to. As it turns out with our sample data, it also turned out to be the best solution. That completes this chapter of the class. Feel free to move on to the next chapter.